Hello and welcome to Live from the Lab. This is the show where we talk about different technologies that Bruker has developed to help scientists understand the world around us. Today's topic is CMOS detectors for X-ray microscopy. Now, if you haven't watched Live from the Lab before, the term X-ray microscopy might actually be new to you. What is an X-ray microscope? Well, what we do is we combine micro CT hardware with software to create an imaging solution. And altogether, we call this an X-ray microscope. Now, one of the essential components of this X-ray microscope is, of course, the detector or the sensor. So today, we're going to dive a little bit deeper. We're going to understand it. In this context, in fact, we're going to look at it in this instrument, the 1272, which is a benchtop unit, and learn a little bit more. Hi, Dave.
Hi, John. How are you this morning?
I am doing wonderful. So Dave is our resident expert in X-ray microscopy. Thanks for joining. And so today we're talking about these CMOS detectors. Now, the first thing, though, I want to address a little bit is this idea of a benchtop X-ray microscope. Because when I think CT, I think, oh, big hospital machine.
Rooms, yeah.
Yeah, really expensive too, right?
Right.
Now, micro CT, okay, fine, a little bit smaller, but still, wow, we're at the point that it can be a benchtop. Huh?
Right, and it really is a benchtop. They fit on a standard lab bench. They're about the size of this table.
Okay, and we actually have three different models, right, that kind of speak to different uses.
Right, yeah, the 1275, the 1273, and the 1272.
Okay, so we've seen the 1275 before on Live from the Lab. That's
Correct.
The one with the push button, right?
That is right. That's kind of your all-purpose instrument.
And what kind of detector does that machine use?
So that uses what we call a flat panel.
All right, so a flat panel is just a flat detector.
Yeah.
Kind of bigger pixels.
It is a type
like this,
of CMOS.
Right? Okay.
But it's different than the CMOS we're going to be talking about today.
All right, and then the 1273. Now, what is the specialty there?
That's the big brother of the 1275.
Yeah, in terms of size, we're talking.
Right, size, power. So, like the 1275 is a good all-around system, but say you are doing larger samples or more dense samples, the 1273 allows you to have a larger sample, it's got a bigger chamber, and it's got a higher power X-ray source.
All right. So then we come to this 1272. And by the way, all three of these, they are benchtops. There is a larger machine, a floor standing one, that's the 2214. That gives you, a little bit more resolution and things like that, but
flexibility.
Yeah, flexibility. So the 1272 though now, right?
Yes.
This machine, what is the specialization for the 1272?
That is your go-to R&D machine. That is going to give us your highest resolution for a benchtop sample.
And what are we talking about here? When you say resolution, are we talking like a millimeter, micron? What is it?
Half of or 5 microns, 4 microns.
Okay, 5 microns.
Yeah.
Now, I've noticed on the website, though, we do list the 5 micron number, but there's also this other number there. There's like 450 nanometers. What is the...
So there's a difference between the pixel resolution, and it's like when you take an image, what size does each pixel represent? Mm-hmm. And then there's the resolution, which is how small of an object you can actually measure.
Okay.
And and on the highest power, if you've listened to our podcast before, or videos before, you'll see that it's getting the detectors far away from the source gives you the max resolution. In that case, 450 corresponds to the actual pixel size, but you're always limited by what is the diameter of the X-ray beam. In this case, it's going to be about 5 microns.
All right. So, and if you want to learn more about some of these resolution effects, there's a great YouTube video, Resolution Effects in XRM, that's on our YouTube channel. So go ahead and tune into that. Now to dig a little bit into this detector specifically. Mm-hmm. So what kind of detector were we using previously?
We were using a CCD.
Okay. And
charge coupled device.
And that's a pretty standard scientific sensor there, right? That's
been the standard for 20 years.
Okay. And then, now what's the difference between this CCD tech and then CMOS? I know in imaging, like in cameras, I go out, I want to buy a camera.
Right.
I've heard that before. Okay, you had CCD and now you have CMOS in these cameras. What's the difference between those techs?
The simple is, there's a couple things. How the charge is collected. So you have a pixel, it collects, it builds up charge as light hits on it. and then you have to collect that to make an image.
Okay.
So in a CCD, you are basically collecting your charge. At some point, you basically drain all of the pixels, and collect that, and then that gets converted to a voltage, and then from a voltage to a digital signal.
All right.
So in a CCD, that's all done by one set of electronics. In a CMOS, each pixel itself has its own amplifier and collection electronics. So when you collect that information, you're collecting it as a voltage, so it's a much more efficient, faster collection and less subject to noise.
All right, so when we talk about the megapixel size on these things, they're like over 10, right? It's like 16 or something, like 16 megapixels. There's actually like 16 million active pixels with electronics and everything like that.
Correct.
In these CMOSs?
Yes.
Really? Wow. I think that just speaks to like the state of
technology,
semiconductor tech right nowadays. Now, though here even we're specialized a little bit more, right? So we had CMOS. Now what about going up to this scientific CMOS or sCMOS? What's the difference there?
So it really is a design philosophy of what you're going to use the systems for. So in your camera, you want to take a picture, you want to collect it really quickly, so you have ready to go again. So a camera CMOS is designed to collect an image quickly.
Okay.
So when we're doing scientific CMOS, we're not really worried about speed, we're worried more about collection efficiency. So in a scientific CMOS, they have a better dynamic range, so they're really designed for long-term exposures and having the least amount of noise under that period.
Okay.
So increasing signal to noise.
All right. And is there any other benefits to this new detector technology?
They're faster, the collection efficiency is better. A CCD, you're actually only collecting 50% of the active chip, whereas CMOS, you're getting closer to 100% of the active chip.
So the field of view on these is actually larger.
Field of view is larger,
Okay.
20%-ish,
Yeah, and one thing that Brooker has done actually in the implementation of this tech is that we actually use kind of a rectangular one, and then you can move it too, right?
Right, and so in the 1272 and the 1273, we move our detector around, so it actually expands your field of view.
All right, so you can measure bigger things, you can get better resolution, just because the magnification, right? You can do better that way.
So you get higher contrast, better collection efficiency, faster scans.
All right. So now that we understand all of those intricacies, what we're going to do is we're going to switch over to our application lab in Belgium, and we're going to actually see this technology in action.
Good day, everybody. I'm Valérie Van Koenberg, application scientist in X-ray microscopy in Brooker. Today, I'm sitting in the demonstration lab in Belgium, next to our benchtop system, the SKYSCAN 1272, the new CMOS edition. Today, we will perform together a high-resolution scan with this system, and then look at the data and compare it with our previous edition, the one with the CCD detector. But first, let's have a look inside the system. As you can see here, the chamber can welcome objects having a size of 80 mm height and 75 mm diameter. So here we have the rotating stage, which is equipped with a macro positioning platform that allows us to control through the software the position of the material, and that allows us to put it right in the center of the field of view. Here at the back, we have also a visual camera that will allow us to visualize the sample inside the chamber, see how close is the sample from the source. On the left side, we can visualize here the X-ray source, which is actually a sealed X-ray source that can go up to 100 kV for a power of 10 watts. So the best focal spot size of this source is about 5 micrometer. And then on the right side, here I especially remove the cover for it, we have our CMOS detector. So this is the part that you see here. And then on the top of it is fixed the filter wheel on which there is 6 positions of filter. So the position of the filter can be controlled automatically by the software, and so far we are on the position without filter. Okay, now that we have a better insight on the system, let's see what we have on the scan menu today. As my background is food engineering, I specially select for you a sample that I really enjoy scanning during my PhD. This is Pringle chips, and you will see that the macrostructure of this product that we really enjoy eating is also very interesting and very complex. Let's have a look. So here I have one entire piece of chips. I can eventually scan if I want it. Actually, it fits inside the chamber. However, as this material is quite big, I won't gonna be able to reach high resolution because the resolution is based on geometry magnification. Larger is the sample, lower will be the resolution. If I want to scan my material in a resolution below 1 micrometer, and that's I want to do today, I need to break my sample, here I show it, in very, very small, tiny pieces, like this one. It's no more than 2-3 millimeter diameter thickness. When it is done, I can just take my sample and then fix it on one of the sample holder tips that we are providing with the system. Here, I fix it with some dental wax. That's just allow the stability of my sample. Once my sample is ready, I can just put it inside my chamber. Here it is. Just push it into the sample holder brace and then tight it in that way. Here it is fixed. So now I'm ready to scan. I can close the chamber. Now my sample is installed inside the system. Let's close the door with the software, the control software, and then let's move on the software interface. Here it is, in order to see how to set up the scan. Okay, the system is almost ready. Now the door is closed, which means that I can switch on the X-ray source, I can switch on the detector, and here we will see our tiny piece of chips. So far we are at the lowest magnification, which is about 6 micrometer in pixel size. I can move my sample closer to the source and that will allow me to increase the magnification. So let's move it as close as possible to the X-ray source. We can see through the visual camera that the rotating stage is adapting the sample position according to the resolution that I set. And here we have our sample right in front of the source. So we can see it there. I will just adjust the position of my sample, try to make it more right in the middle of my detector, make sure that it's occupying most of the part of my detector. Here it's good. I will double check if it's remain in the center of my field of view over the rotation. So I can easily control that with the macro positioning command that I can just adjust with those purple arrow. Here is good. Last check over 180 degrees so that I make a complete half. Here it is. Perfect. So my sample is right on the position. I'm happy with the pixels resolution, which is about 0.8 micrometer, so we are scanning at high resolution, below 1 micrometer. As my sample is very low in density, we see that it's quite transparent on the screen. I'm using low voltage that I already preset here, so I'm scanning at 40 kV. And as I'm ready to scan, as my sample is ready to scan, I can press on the scan button. That will just open a new window with more scanning options. So I will enter the name of my sample, and then I can add some additional parameter, including the rotation step, the frame average that I would like, and other additional options. Here I will press on scan. I'm happy with the parameter that I have. So once the scan is starting, we will have that progress window appearing that just shows the progress of the scan. The live camera is still on so that we can track the rotation over the time. And after grabbing a couple of projection images over several rotation steps, we will have a better estimation of the time. And come back later to see the result. Construction is done. Let's have a look to the result with our visualization software data viewer. And also, we can compare this result made with a CMOS detector with result that I generated previously using a CCD detector. Here we have our tomographic cross-section of the Pringles chips that I just scanned. So we wouldn't expect that, but the microstructure is very complex. So we can recognize the crisp, that's the light gray surrounding, let's say, the product. And then inside we have different and various size of porosity. One very large cavities in the middle, as well as smaller pores at the surrounding. And that overall structure is making the crispness of the chips. If we even look a little bit closer, we can even distinguish two types of pore. We have first the pores filled by air, which is those color coded in black. Here we can recognize few small ones, here a larger one, here as well. And then we have another types of pores which are filled then by oil. Indeed, that's those color codes in dark gray. Here we can clearly recognize the difference between that large pores, color code in dark gray, and this one in dark. But we can even look various ones spread around inside the sample here as well. Basically, that's during the deep fry process. There is oil that is absorbed by the crisp, and that's just trapped inside the high porosity of the material. We can also look through the different cross-section. I'm looking through it. We can see that we have some salts, some salt particle. Was okay. There is some salt on the crisp. That's why we like them. And if I look also, I can also have a look of the 3D structure, or just load the 3D view in the different spatial plan in order to have a better appreciation of the product. Here, this is another view. We can see how complex is the structure. Basically, with image processing, we can isolate the three different parts that we can distinguish inside the chips. We can analyze in 3D the crisp, for example, the thickness distribution of the crisp, but we can also isolate the air pore for the pores filled by oil and measure the filling percentage of oil inside those pores. And that's something that I will show you with our 3D volume rendering software a little bit later. But first of all, I would like to have a quick comparison between datasets taken with our previous edition, the CCD detector, and the one taken with the new SKYSCAN edition with the CMOS detector. Here it is. So, on the left side here we have the dataset taken with CCD detector, and on the right side here we have the CMOS image. In overall, the two images look pretty similar. Here I just took one image to make the visualization easier. But let's have a closer look. To be honest, both of them will be easy to analyze. But what we can see is some difference, slight difference between CCD data, which has some edge brightening. We can see maybe this spike here, that's typically an edge brightening artifact that we won't gonna see with a CMOS images. Something else that I really like and that illustrates very well the quality of the data is the gray shade distribution that appear more uniform for CMOS data, which is in overall a good improvement in the transition of detector. Another thing that we will notice between CMOS and CCD data is that in overall the image quality of the CMOS appears slightly better than CCD. That's something that we can see on that data set. For example, around that bar we have the feeling that the distribution of grayscale and the contrast is slightly better than on that side where it's appear being a little bit more noisy. And that's the type of improvement that we can distinguish between CMOS and CCD, and we are happy to move on to that detector. Finally, as I told you earlier, I perform a 3D analysis in order to analyze the crisp size distribution as well as the pores filled by air and the pores filled by oil distribution. And I plot it and color code it with our 3D volume rendering software CTBox. That's what we can see here. So we can recognize the crisp that has been color coded in orange shade, and then inside it we see in blue the air pores and in red the pores filled by oil. So with that software we can really look through the structure, slicing through in that way. We can appreciate the distribution and even recognize, for example, that the air pores are mainly located in the middle of the sample, while the pores filled by oil would be rather located at the surface of the crisp. That's an absorption effect. So that's with this manipulation of sample that I will finish this result presentation. Thank you for watching this video. Do not hesitate to contact us if you have any more questions. On my side, I really enjoy recording it. So now it's time for me to leave you and also finish this one because I really like them.
All right, so here we are. We're back in the studio, and we're going to answer any of the questions that you have. So on the right side of your screen, you can go ahead and type those questions in, and we'll answer those right now. We also have some questions that actually came in before the stream started, so we'll get through those. But if you have any other questions that we either don't get to, or if something pops up later, make sure to send it to our email address here. That email is live.events@brooker.com. All right, Dave, so just to kick off, we've got a few that had come in. Yep. And the first one is from Tim. So Tim, thanks for sending in this question. Is this available as an upgrade?
The answer is yes. It is available as an upgrade.
All right.
It does require a service visit. Mm-hmm. It's not something you can do yourself. It requires someone to come out. We have to change top of the camera. There's also the boards and the electronics have to be swapped out. Okay. So they can be done on site, or you can actually ship it back to the factory and have it done there as well.
So this is like one of those times that it's actually a great way to reinvest in the tool that you have. This is one thing that Brooker likes to do. We like to take these innovations and offer them to current customers. You would have to check, mm-hmm. depending on your locality. It might be that currently it's just available in the new 1272, but soon will be available.
Right.
depending on when you're watching this video, and also, like I said, your location, just reach out to us and we can help you out with that.
Yep.
But it's a great way to renew a machine. Right?
Exactly.
So,
your X-ray source is going to be good for years, and this way you can upgrade the capabilities of your system for a minimal expense.
Yep, and when the service person either comes in or when you send it into Brooker, not only are we going to go in and just replace that detector, there are some other components, like Dave said, and we're also going to go through that machine and make sure that everything is right, make sure that it's meeting the specs. So it's a great way to kind of...
Good chance to check your software.
That's right.
You know, and something we've brought before is most of our software upgrades are available at no cost online if you subscribe to Brooker Support.
Yeah, and so and that website, by the way, is www.brookersupport.com. If you haven't ever signed up for that, that is a great resource.
It is a great resource for app notes, for little tidbits, workflow, and software manuals. It's all there.
So make sure to go there. Now, one other thing I wanted to note, you did mention sending this in. Of course, this is a benchtop machine.
Yes.
Now, there's a bit of shielding in there, so it's kind of heavy.
Yeah, the 1272 does weigh a couple of 100 pounds.
Yeah, but this is something you can ship back. In fact, when you buy the machine, it's delivered in a reusable flight case.
Yep.
So hopefully you saved it.
And hopefully we told you to save it.
That's right. So you just pack it back up in there, and then you would send it out to us. Now, if you don't have your case anymore, we can help you out with that too.
Yeah.
Getting you a new case. So, next question is from Anita. And the question there is, why do the pictures look clearer on the CMOS?
So, a couple of reasons. The CMOS does generate a better picture. In other words, a higher contrast picture. So you have a greater dynamic range. So you're able to collect more information, covering a greater range, and that does help with the actual sharpness of the image.
Yeah,
and also the CCDs give you a more uniform image. I think Valerie discussed that a little bit too. That
the CMOS.
The CMOS.
Okay, the CMOS does.
The CMOS. Sorry, CMOS does give you a better image overall.
It's kind of like there's this noise factor too, and the way I like to think about it is, if we think back to when we had analog TV, right? Not just the difference between HD and that, but when you actually had analog TV, it was coming over the waves and stuff like that, and you get that little bit of fuzziness, right? But then with the digital signal,
right?
It's really it's all there. It's beautiful. Now, granted, this isn't that whole analog to digital. It's just a metaphor.
Yeah.
But it really clears things up when you take that noise away.
It does.
Right. Lets you see what matters.
Right, and from a speed standpoint, if your signal to noise ratio is better, it means you have to do less averaging. So typically on an XRM scan, you'll do 3, maybe 5 images and then average those images. And so if your image is sharper, you can do less average, so you're getting a cleaner image faster.
So, and one other thing that I remember Valerie kind of pointed out there in the demo was how it really reduced those issues from when you have a really dense area in the sample. Right. And so we used to get, on a CCD, sometimes you would see these artifacts. Right. And those were gone. Right.
Less of, they're gone to a greater, I'm not going to say they're gone, but
they're less apparent.
Right, less apparent. And also some of the scatter events seems to be a little bit cleaner as well.
All right. So it's definitely, a great innovation from that side.
Yes.
So, and then another question that we had gotten in before was from G, and that question is the CMOS faster than a CCD? Now, you just touched on that a little bit.
I just touched on that, yes. They are faster, 30-40% faster.
Okay.
And again, collection is better with a CMOS. The photon flux to a CCD, the CMOS collects more. And then the collection efficiency, all that, so it's like I said, 30 to 40% faster with the CMOS detector.
And there's kind of two types of fast though too, right? There's the, how long does it take me to get to similar image quality?
Correct.
Right? And then there is just how fast in general can I collect a scan? That's always a question, right? People come in, they're introduced to XRM, they go, well, how fast can I get a scan, right?
Right.
This would allow you to get that much faster, right?
Correct.
Just even a basic scan.
Yeah, just even a basic scan is going to be faster with your CMOS detector.
All right. So another question now that has come in, actually right here in the live stream. So Javier, thank you. I wonder if it could be possible to upgrade an 1172.
I have not seen that yet, and to be answer, I don't know. And currently, I think the focus is on 1272 integration. I have not looked into. I've not seen what's going to happen with the 1172s yet.
And in that regards, if you have an 1172, like I said, talk to us, and sometimes it's, we'd also just say, you know what, maybe we're better off upgrading the whole platform, getting you up to the 1272. And if you're a current user, of course, we'll work with you on that, with that machine. Get a trade-in. And now we have the perennial question that everyone wants to know: how much does this cost? It sounds great. What are we talking here?
I actually don't know the current price. I have not seen it yet.
Yes, and I can honestly say I do not have a price. I would not want to throw a number out there. I do not know if this is $10. I'm guessing it's not.
No, it is not $10.
But I don't want to. I know it is in line, with what a detector would cost. So, and also in that we would have to just add in, if you have the on-site service versus the send it in, and there's that component of it.
Yeah.
So I would love to give you an answer to that, Javier, but unfortunately, you're just going to have to reach out. And,
reach out.
We'll get you
in touch with the right person.
That price.
Yeah.
So then another question from Javier. So thanks for all the questions. If anybody else has some questions, please put it in there. He missed a part of the presentation to know the difference in time between two scans comparing the CCD and the CMOS of the Pringles chip. So
I don't remember the time off the top of my head.
Yep. But in general,
it's
if I can collect the same data quality, let's say.
Actually, it's going to be 30. There is a couple images. It's actually about 30% faster and a better data quality.
So what if I want to do the same data quality, Dave?
Probably 40 or 50% faster. I don't know. I've always just done, this is a good quality image, yeah.
So instead of an hour, you're talking 40 minutes.
Right.
And you will get better data quality in that. It is one of those hard things because the CMOS, just in general, is just providing a clearer image.
Yep.
So to get the exact same image, you'd actually have to work really hard.
Yeah.
I don't even know if you could dirty it up enough.
Yeah, maybe you can.
So,
yeah.
Or maybe you have.
Yeah. I always do a really, really fast scan when I get a sample, so yeah, you can make that then.
All right, so with that, it looks like we don't have any other questions that have come in. But thank you out there to everyone for joining. And thank you, Dave, for joining us on Live from the Lab.
Yeah.
And thank you to Valerie in Belgium for our demonstration of the instrument in action. And until next time, we'd like you to keep your signal high and your background low.